Thank you for your interest in hyperspectral multispectral image fusion and in Physical Sciences Incorporated. I'm Chris Gittens, and I'll be telling you about our Phase 2 SBIR program with the Naval Sea Systems Command to develop hyperspectral multispectral image fusion to support detection and localization of minefields and obstacles in the surf zone and beach zone. The program is supported by the Naval Sea Systems Command, but the opinions, findings, and recommendations expressed here are my own and don't necessarily reflect the views of Naval Sea Systems Command. Physical Sciences Incorporated is an employee-owned small business headquartered in Andover, Massachusetts, approximately 25 miles north of Boston. PSI was established in 1973 to provide integrated experimental, analytical, engineering, and product development capabilities to government and industry, with the ultimate goal of technology transition to a broad range of user communities. PSI conducts a wide range of basic and applied research, engineering, and product development in the areas of materials and structures development, radiation, photonic, and optical detection technologies, aeronautics, network systems, life sciences, and robotics. Our 275-person staff is highly interdisciplinary and includes people with degrees in physics and applied physics, organic and physical chemistry, chemical, electrical, mechanical, and optical engineering, applied mathematics, and computer science. Approximately half of the technical staff is at the doctoral level. Our research and development operations are conducted within our optical systems, material systems, and applications divisions in Andover, as well as our research support instruments and Faraday Technology subsidiaries in Lanham, Maryland, and Clayton, Ohio, respectively. We have additional operations in Haverhill, Massachusetts, Wilmington, Massachusetts, Epping, New Hampshire, and Pleasanton, California. We're a leader in transitioning technologies developed under the Small Business Innovation Research Program. As of December 2021, we secured more than $736 million in SBIR Phase 3 funding, product sales, and third-party investment. For completed projects which are not yet at the market insertion phase, for every dollar invested by the government, PSI has secured more than 3 times that dollar investment in outside funding. Our multispectral hyperspectral image fusion program addresses the Navy's need for improved detection of beach zone and surf zone minefields. Specifically, we're addressing the need for more effective airborne reconnaissance prior to an amphibious assault. Optically based sensors are well suited for deployment on UAVs. That noted, neither multispectral nor hyperspectral sensors are optimal for the landing zone reconnaissance task. High spatial resolution multispectral imagery typically doesn't provide sufficient spectral information to enable reliable target detection with sufficiently low false positive rates. Conversely, while hyperspectral imagery provides spectral data necessary for detecting objects of interest based on color, it can lack the spatial detail necessary to discriminate targets from non-targets. Fusing spectrally rich imagery with spatially detailed imagery results in a high spatial resolution, high spectral resolution image product, which can be used to create a high-fidelity map of landing zone mines, obstacles, and minefields when processed with an appropriate automatic target recognition algorithm. While the image fusion algorithms we're developing are generally applicable, we focused on fusion of imagery collected by sensors being developed under the Navy's Coastal Battlefield Reconnaissance and Analysis Program, otherwise known as COBRA. Those sensors are a visible through short wavelength infrared hyperspectral sensor developed here at Physical Sciences, and a 6-band multispectral sensor developed by Arete Associates. We're currently testing the fusion capability and evaluating the benefits of fused imagery for mine detection using flight test data acquired at a government test range. In the top half of this slide, you see an example of fusing a high spatial resolution grayscale image with a lower resolution color image to create a high spatial resolution color image. Specifically, we're showing fusion of a high spatial resolution panchromatic visible image with a lower resolution multispectral image collected by the space-based Worldview 3 sensor. The fusion product combines the spatial resolution of the broadband visible image with the spectral content of the low spatial resolution multispectral imagery. The resulting image enables effective exploitation of shape and color for object detection and identification. For example, one might identify the two school buses in the panchromatic image based on their shape, or in the RGB image based on their color, but their identity is unambiguous in the high spatial resolution color image. Fusion of high resolution broadband visible with lower resolution visible wavelength multispectral imagery is commonly referred to as panchromatic sharpening, also pan sharpening. There are many different pan sharpening algorithms, some of which are suitable for fusion of hyperspectral and multispectral imagery, and others which are not. For our work, we've evaluated a wide variety of panchromatic sharpening algorithms using field test data and identified the ones best suited for hyperspectral multispectral fusion. Since this chart was created in August of 2022, the government has exercised the Phase 2 option program. The program was originally scheduled to conclude in March of 2023, but will now run through September 2023. While I've been speaking to hyperspectral multispectral image fusion, our program has 2 algorithm development tracks. Track 1 is image fusion. Track 2 is spectral spatial-based target detection using the high spatial resolution hyperspectral imagery produced by the fusion process. As I stated early on, we've leveraged public domain fusion algorithms for our work. We performed an initial evaluation using ground-based measurements made at our Epping, New Hampshire test range. We identified the best performers based on that evaluation, tailored them for our application, and since the summer of 2022, have been evaluating them using imagery collected during flight tests at U.S. government test ranges. Fusion algorithm enhancements are in process, and we'll begin refactoring the code to optimize for speed and real-time processing shortly. On the target detection algorithm track, we've developed a new approach to exploit both the spatial and spectral content of high spatial resolution hyperspectral imagery. Our detection algorithm development is ongoing and is scheduled for completion in summer 2023. Our immediate application is detection of mines and minefields and beach zones and surf zones. The high spatial resolution hyperspectral imagery created using our fusion processes and analyzed using our target detection algorithms will significantly improve mine detection capability relative to using low spatial resolution hyperspectral or high spatial resolution multispectral imagery alone. This will improve the Navy's ability to conduct unmanned aerial tactical reconnaissance in the littoral battle space prior to an amphibious assault. Detection of mines and minefields are one application of the technology. More generally, hyperspectral multispectral image fusion and associated image processing capability enables more effective detection and identification of objects based on their shape and their color. Our approach to transitioning to the fleet has been to integrate with sensors developed for the Navy's Coastal Battlefield Reconnaissance and Analysis Program. Specifically, we've tailored our fusion processes to work with hyperspectral imagery collected by our own VNIR through SWIR sensor and Arete Associates high spatial resolution multispectral imaging sensor. The program is approaching the end of its second year and will conclude in fall of 2023. Between now and program completion, we'll continue to refine our spatial spectral target detection algorithm, as well as to identify processing architectures for real-time implementation. We envision the development and testing of a real-time processor will occur in a subsequent effort. We envision that the image fusion capability we're developing will have commercial application as a plug-in to third-party software such as Envy, PCI Geomatica, or Socket GXP. We believe that the primary commercial market for that capability is creation of imagery products from imagery collected using space-based sensors. Market researchers predict over 10% annual growth in the satellite remote sensing market over the next few years to achieve a total market value over $5 billion. We had preliminary discussions with an imagery provider at the start of the program and will re-engage now that we have more mature fusion capability. Thank you again for your interest in this hyperspectral multispectral image fusion and exploitation program. Thank you also for your interest in Physical Sciences Incorporated. We have a long history developing spectral imaging sensors, image processing algorithms, and real-time signal processing solutions. Please contact me at the address below to discuss your application and how we can provide a solution.